Now, in this lesson, we are going to focus on models, but specifically linear models. And when we talk about linear models, they're going to be straight lines. Okay? So, and when we talk about an equation of the line, in this class, we're going to focus on what's called slope-intercept form of a line. And this is your slope, your m, and b is your y-intercept, which is why this is called the slope-intercept form of a line, because you can quickly identify your slope and your y-intercept. The slope is going to be always the value that's in front of your x, and your y-intercept is always going to be the value that's not with the x. Your y and your x will remain in the formula or in the equation because that's where you're going to input and output things. What's going to change from situation to situation or problem to problem is the m and the b. Remember that your y is your output or your dependent variable, and your x is your input or your independent variable. So let's talk about m and b now. M is the slope of the line, and the slope of the line will tell us two things about the line. If you look at the sign of the slope, whether it's positive or negative, that will tell us which way the line is tilted. If it is a negative slope, then it's going to be tilted in such a way that if you trace it going from left to right, it will be going down. If you have a positive slope, that means the line is going to be tilted in such a way that when you trace it left to right, the line will be going up. So slope tells us the direction that the line is tilted, but then it also tells us the steepness. If you ignore the sign of the slope for a moment and you just focus on the number, the bigger the number is, the more steep the line is going to be. Now, when we're talking about the slope in the context of some problem, which is what we're going to really focus on in this section, we call it the rate of change, which is going to be the change in the y quantity, whatever that y quantity represents, and the change in the x quantity. So we're going to take the change in the y quantity and divide by the change in the x quantity. And excuse me, it looks like I forgot my e's there. So now one thing we're going to stress in this section too is if we're talking about a linear function, that rate of change or your slope has to be constant, meaning it's not going to change. That steepness and that tilt is going to remain the same. So if I look at something that's linear, so notice I have 4 points here. I labeled them 1, 2, 3, 4. If I find the tilt, the direction of the tilt and the steepness between 1 and 2, it's going to be the same steepness and direction of tilt between 3 and 4. However, if I get something that's not linear, that's not guaranteed no matter which 2 points I pick. So if I pick these 2 points here, this steepness and tilt is going to be different than this steepness and tilt. So when you're talking about a linear function or a linear model, that equation is going to have to maintain a constant slope in order for it to be considered linear. Okay, so we already talked about this a little bit, but I want to go into it in more depth so you can see some of the special cases. So types of slope, there are 4 types of slope. There's a positive slope, which is what we talked about, right? If your m, the value that's in front of your x, is a positive number, then it's going to be tilted so that when you trace it left to right, it's going up. If your slope is negative, so maybe you have a slope that's -2. Okay, so the number that's in front of your x is -2. If it's negative, that means if you trace it going left to right, it's going to go down. So these are the most common slopes that we're going to run into, but we have some cases that you might run into that are special cases. If you have a horizontal line with no tilt, then the slope is going to be 0. If you have a line that's a vertical line, that slope is called undefined, because what you're doing is you're going to be dividing a change of x, which is 0. So you'll be dividing by 0, which is undefined. Now, we talked quite a bit about slope. Let's talk about y-intercept. The y-intercept, which is the value of b in your y equals mx plus b. Here's my slope-intercept form. We talked quite a bit about slope so far. That's my value of m. My b is my y-intercept. So that's going to be where it crosses the y-axis, which means since it's crossing the y-axis, it's the value of y when x is 0. So in this case, this example right here, it's crossing my y-axis at 2, so my b in this case would be 2. If we're talking about it in the context of a problem, like a real-life problem, then the b is called the initial value, because typically in real life, we don't talk about negative time or negative money. We don't talk about what happens on this side of the graph. We're only looking at the positive side. So on the y-intercept, we're starting at the point 0. That's why it's called our initial value. So when we're talking in the context of a problem, our b is going to be the initial value, which is really the y-intercept. So my b in this case would be 2. If we want to find the slope and we're given a graph, we can see what the change in y is over the change in x. My change in y is the change in my vertical distance. So I'm going from 2 to 4. So I'm going up 2. So my vertical distance is a change of positive 2. My horizontal distance is my change in my x. I'm going from 0 to 3. That's from here to here, to go from this point to this point. So my change in x would be 3, which means my slope would be positive 2/3. And I can check to make sure that it's positive, because if I trace this going left to right, it's going up. So I want to make sure that the sign of my slope matches the tilt of the graph. Okay, let's look at our first example. It says, consider the graph below. On the x-axis, we have time in hours, so that's going to be our independent variable. That's our time in hours. Our dependent variable is the rain depth in inches. That's our quantity on the y-axis. That's our output. So that's dependent. So that's the rain depth in inches. So it says, describe the function shown on the graph. We already noticed what the dependent and the independent variables are. And if we look at it, this function describes the relationship between the time and the rain depth. Now, if we look at it closer, if we start at 0 time, we have 0 inches of rain. If I look to see someplace that it crosses exactly, I don't personally like to check places that it doesn't cross exactly if I have the option to pick one of these points, because it's hard to tell if that is, say, 1.4 or 1.5. So I try to find and use points where it crosses exactly. So if you notice, in the course of 3 hours, this point right here represents that in 3 hours, we got 1 inch of rain. Now, if this is truly a linear function, that rate should stay the same. So if I go over another 3 hours, if I come over to 6, I should go up to 2 inches. I should have gained another inch from 1 to 2, which it looks like if we continued that, it would match that prediction. So we could describe this function as a relationship between the time and the rain depth by saying about every 3 hours, the rain depth increases by 1 inch. And another way to say that is that the rate of change is 1/3 inch per hour, because we're looking at Remember the change in Y quantity, and the Y quantity is the change in the rain depth. And we divide that by the change in X quantity, and the X quantity is the time in hours. So it goes 1 inch every 3 hours. So I would write that as 1/3 inch per hour. So the rate of change, or what the slope represents, is how much, what the rate is per hour of how much rain we're getting. Part C says, discuss the conditions under which a linear function is a realistic model for this given situation. So this would be a good fit, meaning it would remain a good linear function that models the situation as long as the rate of rainfall stays constant. So if for some reason 2 hours later it starts raining more heavily or it slows down a little bit, then this linear function isn't going to work to model the situation, because we need to make sure that that rate of rainfall stays constant in order to measure it appropriately on the graph. Okay, let's look at example 2. Consider this graph below. We have on the x-axis the time in hours, and then on the y-axis we have the distance from home in miles. So the independent variable is going to be the time, and the dependent variable is going to be the distance from home in miles. And to describe this function, we can definitely say that there's a decrease, because if I'm looking at this, it's going down left to right as I trace it. So this is going to have a rate of change that's negative. And I can describe this by saying, if I look at where it crosses exactly, you can pick any 2 points as long as it crosses nicely and it's easy to read. This point right here is 900. And that's at time 0. This point right here is at 7 hours, but it's at a distance of 0 because it's on the x-axis. So what this is telling me is it decreased 900 miles in 7 hours. So that's how we can describe this function. We can say this function describes the distance from home at a given time, and the distance from home decreases by 900 miles every 7 hours. Now, if we want to find the slope of the graph, that's the rate of change, which we already looked at on the graph. It's the change in y over the change in x, and the change in y represents the change in miles from home. The change in x is the change in hours, and we said that 900 miles, it decreased 900 miles in 7 hours. Okay, and because it's decreasing, I gotta make sure the slope is negative. So when I answer this, according to the directions, it wants it answered to the nearest tenths place. So when I divide that and I take negative 900 divided by 7 and I round it to 1 decimal place, I get negative 128.6 miles per hour. The negative just means it's decreasing, so we're getting closer to home. Now, this concerns me, the 128.6 miles per hour. Someone's going super fast on the highway and going way over the speed limit, or hopefully they're on a train or something else if they're going that fast. Okay, let's look at part C. Discuss the conditions under which a linear function is a realistic model for the given situation. So this would be a good model if the speed remains constant. If this speed starts changing, we're not going to have a line anymore. We're going to start to get different curves. In this next example, it says that the cost of publishing a poster is $3,000 for setting up the printing equipment plus $2 per poster printed. And it says the situation can be modeled by a linear function. So we have 2 variables here. We have the cost of printing, and then we have the number of posters. So the cost is going to depend on the number of posters. So we're going to list the cost as the dependent variable, and the independent variable will be the number of posters, which means the rate of change, or the slope, is going to be the change in the cost, because that's my dependent, over the change in the number of posters, which is my independent. So it's the change in cost over the change in posters. That's given to us in the problem. It says it's $2 for each poster. So this is how these two quantities are related. So this is going to be the slope. So that's what's going to go in front of my x. Now our b is the initial value, and it says it's $3,000 to set it up. So that's going to be my initial value. So I have my m, which is 2, and my b, which is 3,000. And so my equation is going to be y equals 2x plus 3,000, where I would plug in the number of posters, because that's my independent variable, and I would get out the cost based on the number of posters. Now to graph this, I'm going to plot some points. I know for sure I have the point 0, 3,000, because that's my initial value. So at 0 on my x-axis, I'm going to plot the point 3,000. That's my y-intercept. So I'm going to plug in values. Now you can pick whichever values you want. I picked 1,000, 2,000, and 3,000. So I plug those values in for x. When I plug in 1,000 here for x, I get 2 times 1,000, and then I add 3,000. That gives me 5,000. And then I repeated that process for 2,000 and 3,000. So once I got some xy points, I plotted them on the graph. At 1,000, I went up to 5,000. That's this point here. At 2,000, I went up to 7,000. At 3,000, I went up to 9,000. And then I can connect the dots to make my line. Now it says find the total cost to produce 3,000 posters using our model. What they mean by that is to make sure that we use the equation we came up with. So the number of posters is 3,000, which is my value of x. So I'm going to put 3,000 in here. I'm going to multiply it by 2 and add 3,000, which is going to give me 9,000, which we did find that point up here previously when we were graphing points, but that's just a coincidence. Most of the time that won't happen. But using the model, you want to plug it in for x and see what you get out for y. So to produce 3,000 posters, it would cost $9,000. Is this linear model reasonable for the situation? As long as the cost per poster remains the same, then this model will be a good estimation of the situation. We want to make sure that this rate, our slope, stays constant. And that represents the cost per poster. So as long as the cost per poster stays the same, this equation will work. Okay, let's look at the next example. We have the amount of sugar in fermenting batch of beer decreases. Now, this is important. If it decreases, that means we're going to have a negative slope. And it decreases with time at a rate of 0.1 grams per day. So this is our rate. We're comparing quantity of grams to each day. So I'm going to have grams as my dependent variable, and I'm going to have time in days as my independent. And since it's decreasing at a rate of 0.1 grams, my slope, or my rate of change, is going to be negative 0.1 grams per day. That's my slope. Now it also says it starts from an initial amount of 4 grams. So that's going to be my value of B. That's my starting amount, 4 grams. So when I set up an equation, I have my M, which is negative 0.1, and my B, which is 4 grams. My X is the number of days, which is my independent variable, and my Y is the amount of grams after X days. Now to graph this, I plotted some points. So I plugged in 0, 10, 20, and 30 in for X and saw what I got out for Y. When I plugged in 0, I got 4, which that should be a point on the graph because that's my initial value, 0, 4, that's my Y-intercept. When I plug in 10, I get 3. When I plug in 20, I get 2, and when I plug in 30, I get out 1. So when I plotted these points, I got a picture. When I trace it left to right, it goes down, which matches the slope. Remember, if it's a negative slope, it should go down left to right. So this picture makes sense with the situation. So here's my graph. After I plotted these points, when is the sugar all gone? So that means there's 0 grams of sugar. So Y is going to be 0. And we want to figure out when that happens. How many days did it take for it to decrease to 0 grams? So in this case, we are going to plug in 0 for Y because we know that Y should be 0 grams if there's nothing left. And we're going to solve this for X to find how many days it takes. So I have to subtract 4 from both sides. If I want to solve this for X, I'm going to subtract 4 from both sides. And then I'm going to divide by negative 0.1 on both sides. And a negative divided by a negative will give me a positive. And when I take 4 divided by 0.1, that's going to give me 40, which means 40 days. And if I look at the graph right here, the graph hit 0 at 40 days. So there's 0 grams of sugar left after 40 days. Is a linear model reasonable for this situation? And of course, as long as the sugar consumption stays at a constant rate, yes. Next example, we have the following situation can be modeled by a linear function. And it says for a particular model, the price of a new car is $24,000 today, and it rises, meaning increases, with time at a constant rate of $1,080 per year. So we have the price of the car as a variable, and we have the year as a variable. Since this is claiming that the price changes depending on the year, our dependent variable is going to be the price, and our independent variable is going to be the year. Now, our rate of change is going to be how these two quantities change with respect to each other. So we have the change in price, that's my change in my dependent, over the change in my independent, the change in the years. And they told us that in the problem that it was a change of 1,080 per year. And that is an increase or rising, so this should be positive. It's not decreasing, so this should be a positive. And our initial value where it starts at was 24,000. So when we set up an equation for this, where Y is the price and X is the number of years, this is our slope. That's our rate of change that goes in front of the X. And then here's our initial value, which is our B. Now, it says write an equation for the linear function using P for price and T for time. So, if you notice, I made a mistake here. I should have followed the directions. I should have put a T here instead of an X and a P here for the price. So basically what they're saying is Instead of using X's and Y's, they want us to use P's and T's. So just make sure you write that down on your paper because clearly I made that mistake on here. So this should be a T and this should be a P. Now it says how much will a new car of this model cost in 3.5 years. We're going to round to the nearest dollar and use our model. So here's our model. It's the P equals 1080T plus 24,000. 3.5 is going to go in for the number of years. That's right here. And then we're going to figure out what the price is. So we're going to take 1080 times 3.5, and then we're going to add 24,000, and we get 27,780. Now, this one's different from the ones that we have done so far. It says, is this linear model reasonable for this situation? In this case, I would disagree that this is a reasonable model for this situation because typically, if you have the same model over a period of time, a certain model car, usually the price decreases or the car depreciates in value. And in this model, it's saying the price goes up. So to me, I would say that this is not a good model. The following situation can be modeled by a linear function. It says the cost of leasing a car is $1,400 for the down payment and the processing fee, plus $370 for each month. So we're comparing the price versus the time and months. And the amount that we have to pay is going to be dependent on the time and months. So the dependent variable here is going to be the amount that we're going to pay, and the independent variable is going to be the time and months. The slope, or the rate of change, is going to be the change in the dependent variable over the change in the independent variable, which is the change in the cost per the change in the months. And they give us that value here. It's 370 as each month passes. So our y-intercept, or our b, and that's the initial value which they give us as 1,400. So this is our b. So when we put this together and we create our model, thank goodness I followed the directions in this one. It says T is for time, so that's our independent variable, and that's our time in months, and then P is the price, and for the dollars paid here. That's how it's labeled here. So we're going to set it up. Instead of using Y, we're going to use P for price, and we're going to have 370 times the number of months, which is T, plus our initial value. So here's our M, here's our B. Now, for how many months can you lease the car with $5,890? So how long is that going to last with this renting of the car? And it says to round to the nearest integer, and we're going to use the model. So here's the model that we come up with. Now they're giving us the price. That's the 5,890. So this is my P. So that's going to go in here. And we need to know how long it's going to last, how many months. So we're solving for T. So to solve for T, I'm going to subtract 1,400 from both sides. That's going to give me 4,490 is equal to 370 T. Now to solve for T, I have to divide both sides by 370. When I do that, I get T is 12.1351. Now this is in months, but remember the direction said to round to the nearest integer, so we're going to round to 12 months. Now it asks us, is a linear model reasonable for this situation? And I would say yes, as long as the price per month remains constant, just like in all the other examples. As long as we have a constant value and it makes sense with the situation, then we're good. Suppose your dog weighs 2.7 pounds at birth and weighs 15.8 pounds 1 year later. Based on these two data points, or you can call it ordered pairs, we're going to find a linear function that describes how weight varies with age. We're going to use W for weight and A for age. So we have two variables here, weight and age. Weight is dependent on age. So A, our age, is going to be the independent variable, which remember, even though we're labeling it as A, it's like our X, our input, and our weight is W, which is like our Y, our output. Now, in this question, it gives us different information, but we still have enough information to figure out what we need to create our model. So instead of giving us our M and our B, our initial value and our rate of change, they're giving us enough information that we can take and do a few extra steps to figure it out for ourselves. Now, at the point of birth, the dog weighed 2.7 pounds. So right off the bat, I know that that's my initial value. B is going to be 2.7. Where we have to do a little extra work is to find the slope, because they don't tell us how the weight and the age change with respect to each other directly. So remember, the slope is the change in my dependent over my change in my independent. And remember, my dependent is my weight. So if I go from the year 0 birth to 1 year, and I go from 2.7 pounds to 15.8 pounds, how do my pounds change? Well, I go from 2.7 pounds to 15.8 pounds. That means I go up by 13.1 pounds. So that's my change in my weight. Now, the change in my years, or the change in my age, that's my independent, should go in the denominator. So to go from birth to age 1 is a change of 1 year. So the dog's weight changes 13.1 pounds per year. So we can write the slope as 13.1. So we had to do a little bit of extra work to find the slope, but we're using W for weight. A is for age. Here's my slope. We found that to be 13.1, and our initial value is 2.7. So here's the model we come up with. So I plug in the age and it gives me the weight. We're going to use this function to predict the dog's weight at 5 and 11 years of age. We're going to round to the nearest tenth of a pound. Okay, so at 5 years old, the age is 5. So we're going to plug in 5 for A. That goes in here. So I'm going to take 5 times 13.1 and then add 2.7. That's going to give me 68.2 pounds at 5 years old. For 11 years old, we're going to do the same thing, but we plug in 11 for the age. So we take 11 times 13.1, and then we're going to add 2.7, and that gives us 146.8 pounds. Now, would this model work for all ages? This would be a no, because at some point, the dog's weight is going to level off and become steady. He's not going to continue to gain 13.1 pounds per year after he becomes an adult dog. So in other words, he's not going to keep gaining 13.1 pounds until he dies. At some point, it's going to level off. So this model is only going to work up until when the dog's weight levels off and he becomes an adult. Then after that, this model will not work anymore. So this is a really good point to bring up when we talk about models, even if it's no matter what kind of model it is. Under the circumstances, a lot of times that model will only work for a certain period of time. And once you go outside of that range of time, it doesn't work anymore. So you've got to keep that in mind when you're dealing with models, that at some point it might not make any sense. $1 washing machine and a laundromat is depreciated for tax purposes at a rate of $95 per year. Because it says it's depreciating, that means it's going down in value. So when we set up our equation, we want to make sure that there's a negative in front of that $95 per year because it's going down $95 per year. So find a function for the depreciated value of the washing machine as it varies with time. Answer in slope-intercept form using V for the value and T for the time. So we have two variables here. We have the value of the washing machine. We have the time in years. So V, the value, is going to be the dependent variable because it depends on the time. And T, the time in years, is going to be the independent variable. The change in the value per the change in time, that's our slope or our rate of change that was given to us in the problem as it decreases $95 per year. So this is going to be a negative 95 for our value of M. Now our B, our initial value, it says the washing machine starts at a value of $1,290. So when we set up our equation, we're going to have V equals, here's our M, that's negative 95, times our T, which is the number of years, plus our initial value, which is 1,290. When does the depreciated value reach $0? We're going to use the model and round to the nearest year. So we're going to assume that the value is 0 and figure out the time that happens. So that means I'm going to plug in 0 for V and solve for T. So to solve for T, I'm going to add 95T to both sides. So I get on this side of the equation, positive 95T is equal to, and I'm left with 1290 on the right. And then I'm going to divide both sides by 95, and I'm going to get that T is equal to 13.5789. Now it says to round to the nearest year, so that means I'm going to round it to about 14 years is when the value of the washing machine becomes 0. The next two examples are pretty similar, where we're given an equation and we have to identify the slope and the y-intercept and graph the equation. So it says for the following function, find the slope of the graph and the y-intercept and sketch the graph. So remember, the slope is the value that's in front of the x. A lot of times when I ask students, given an equation like this, and I'll say, what is the slope? And they'll answer 2x. The x is not part of the slope, so make sure you're only using the number that's in front of the x. So in this case, our slope is 2. That means for every vertical change of 2, there is a horizontal change of 1. Even though it's not written here, you can write this as 2 over 1 is the same thing as 2. So for every vertical change of 2, we go over 1. The y-intercept is negative 5. That means it's the initial value, so that's where it crosses the y-axis. So that means when we look at the y-axis, we're going to have a point right here. That's my y-intercept at negative 5. So we have the point 0, negative 5. That's my y-intercept. You could also plot some more points using the equation, find the corresponding values of y to plot points and connect the dots, or you can just use your initial value and your slope to graph. If I use my initial value and slope, here's where I start, and I go up 2 over 1, up 2 over 1, up 2 over 1. Although my zigzags don't look very even, but you guys get the point, right? I go up 2 over 1, up 2 over 1. That makes the steps or the steepness. And it should go up left to right because it's a positive 2. So you can just use this information to graph it, or you can use your points that you make in an XY chart to graph it too. It doesn't matter. Okay, looking at this next one, it's the same idea. We're going to identify the slope and the y-intercept and then use it to graph. So the slope is what's in front of the x, so that's -3, which means, because it's a whole number, we can write it as -3 over 1, which means it's going to go down 3 into the right 1. It's going to go down left to right because it has a negative slope. Our initial value is at -4. That's my b, my y-intercept. So I can plot some points and then connect them with the line, or I can start at -4 and say I'm going to go down 1, 2, 3 over 1, down 1, 2, 3 over 1, and I can do it that way to make my line. If I start at this point, no matter what, my rate has to be the same, although my line is crooked because I'm not the best artist. The points should line up. So if I start here, I go down 1, 2, 3 over 1, down 1, 2, 3 over 1. Okay, so using this information, I can draw the line, or I can just set up an XY chart with some points and using this equation to find the corresponding value of Y. So for example, to find the corresponding value of X here, I'd plug in 1 for X, and I have it -3 times 1 is a -3, and when I subtract 4, I get -7. So that's how these ordered pairs come about. So you can just plot some random points and connect the dots. All right, now this last example is going to take some explanation. This is going to be an example of what we call linear regression. Now, in real life, when we collect data and we plot them on a graph, it's not going to come out to be an exact line because things in life are not perfect. But if we want to estimate the closest line to all the points, to use that line to make predictions and estimations like we have in the previous examples, there is a mathematical process called least squares regression, or the line of best fit. And it's a very complicated process with a lot of arithmetic. But I'm going to show you how you can do this on the calculator. And what the calculator does is it uses that complicated arithmetic process to find the line that comes closest to all of these points. So I'm going to need the calculator, so make sure you take a minute and pull out your calculator, and you can pause the video if you need to go look for it. But what we have here in the problem is tells us X represents the weight of cars in hundreds of pounds, and Y represents the miles per gallon for that car. So this point right here, this XY point, represents a car that weighs 2,500 pounds that gets a miles per gallon of 23.4. So these are ordered pairs. We're just looking at it horizontally, then vertically. Now, to use the calculator to find the line that comes the closest to all these points, what we need to do is first enter the data in on the calculator. Now, to do that, you're going to hit the Stat button that's right here in the middle. And then you're going to choose Edit for option 1. If there's data that's already in there, you're just going to go ahead and highlight L1, and then you're going to hit Clear, Enter. You can do that for L2 as well. You would just go up to L2 and hit Clear, and then Enter, and it will clear the whole entire column. In your L1 column, that's where you're going to put all your X's. In your L2 column, you're going to put all of your Y's. I already had mine in here from when I worked through the problem, but I cleared out L1 to show you how to clear that out. Now I'm going to have to go back and put all my X's back in there, which is good because this will show you how to do it. So I want 25 to match up with 23.4. So I want 25 to be here. So I'm just going to hit 25 and then Enter. and then I'm going to hit 28 and enter, and then 31 and enter. And I want to make sure that my XY points line up. I would definitely take your time and go slow and make sure you got these typed in correctly, because if you don't type them in correctly, your answer is going to be off. So I definitely recommend taking your time and double checking everything. Once you get your L1 and your L2 set up with your X's and your Y's, then we want to take a look at the data. So we can tell the calculator to graph this data by accessing the option above this Y equals that says stat plot. So to access it, we're going to hit second and then Y equals. Now we want all of the plots to be off except number 1. Okay, because we graph too many things at once, it gets hard to see and things overlap. So we only want one graph on at a time. So I'm going to hit on number 1. I'm going to hit enter, and I'm going to make sure this says on. On the type of plot, you want to use the scatter plot. So that's this first option here. You want to tell the calculator that you put your X's in list 1 and your Y's in list 2. Now, if it doesn't say L1 and L2 here, to change that, you can see that your L1, L2, L3 are above 1, 2, and 3. And your L4, L5, L6 is above your 4, 5, and 6 buttons. So if you need to access L2, then you want to hit second 2 to get that shift for L2. Then for the mark and the color, you might not have those options on your calculator, but if you have them, it's just your preference. You can pick what you'd like. Now, once you have this set up, you hit zoom, and then option number 9, it says zoom stat. Option number 9, and this will automatically adjust your window so that you can see your values. So these are all your points for these XY points here. Now, if I hit trace and I use my arrows, it will toggle back and forth between the points, and I can see down here which point that I'm sitting on. So this point right here is the point 3715.27. So that's this point right here, 37 and then 15.27. So as you can see, this is not a really good linear graph. The points don't line up so that it looks like a line. And this is what I was saying, like in real life, the data is not going to look exactly linear. And this actually, to me, doesn't look anything like a linear function. But if you need to find a line that comes the closest to all of these points, now what you're going to do, that you've got to look at the graph, you're going to hit the stat button. And this time you're going to go over to this menu here that says calculate. And you're going to scroll down and choose option number 4 that says LinReg for linear regression. So choose option number 4. So I want to make sure that L1 is where my X list is. And I want to tell the calculator that my Y list is in L2. You access L1 and L2 above your 1 and your 2 button. You would have to hit the second button first, like a shift, but you can access your L1 and L2 above your 1 and 2 button. So make sure your X list says L1 and your Y list says L2. Frequency list and store your regression equation, you can leave that blank. That's more sophisticated features that we're not going to cover in this class. Once you tell the calculator that you're using L1 and L2 for your X and your Y list, you're going to go down and hit calculate. Now, if you have a different model calculator where it comes up to your home screen and it says LinRegress, you're just going to do L1, then you're going to hit the comma button, and then you're going to hit L2. And that will do the same thing. Okay. And then, so for this model, I'm going to hit calculate. And it tells me that the general equation is y equals ax plus b. The calculator uses a instead of m, but just remember that value in front of the x, no matter how it's labeled, that's your slope. And it tells us that our a, which is our slope, is negative 0.3605952381. And it tells us that our b, our y-intercept, is 30.02452381. Now, this question tells us to round to 3 decimal places, so we want to make sure that we do that. So when we write down our equation, we can write it down as y equals negative 0.361. That was the a, or our m, the slope that goes in front of the x. And then here's our b. We write that down as 30.025 because we rounded it to 3 places. Now we can use our regression equation to predict the miles per gallon when the vehicle's weight is 4,500 pounds. So we can use the equation to make an estimation. So since x's are already in hundreds of pounds, we just need to put in 45 for x, negative 0.361 times 45 plus 30.025. We get approximately 13.78 miles per gallon. Is that going to be what happens exactly? Absolutely not. This is just an estimation, and we're using our linear model to do that. So we're estimating that a car that weighs about 4,500 pounds should get a MPG that's about 13.78. Now, if you want to see your equation overlap with your points, you can do that by clicking on the y equals button, and you can enter your equation in here. Now, when you enter your equation for negative, you want to make sure you don't use the minus sign. You use the negative button next to the enter sign. So I'm going to put in negative 0.361. For my variable button, for my x, I'm going to choose this button right here next to the stat button. It says xt theta n. That's your variable button. So hit that for x. And then plus 30.025, and I'm going to hit enter. Now, when I hit the graph button, it will show both the line and the data values at the same time. So this is the line for this equation that we came up with that comes the closest to all of those points. Now, there were a lot of steps on the calculator for this, so I definitely suggest that you take notes on step by step of what you do to find your linear regression line, and keep this video on hand to refer back to if you need a refresher.